QI is this. QI is what we call generalized coordinate. What is generalized coordinate? A generalized coordinate can be a linear displacement. It can be angular displacement because it's generalized. So it can be anything. Sometimes you can choose velocity if your problem is of higher orders in its nature. But here, the example is it could be S or theta. So when you take displacement as a generalized coordinate, you simply just replace this replace QI with S. Now what is S dot? S dot means the time derivative of displacement, right? Then what do we get? That's velocity. Therefore, if you put S, if you use S to be, well, QI to be S mathematically, then we have the following formulation, which is the time derivative of this whole thing, partial L, partial V. Because S is displaced, S is QI, and the S dot is just V, right? Minus partial L, partial S must be 0. That's the case when I use S. Now, if I use theta to be the generalized coordinate, what happens? If you do that, this formulation becomes, again, time derivative of partial L, partial omega, minus partial L, partial theta to be 0. And here you can see the power of generalized coordinates, because I don't want to say this is only true for linear displacement. I don't want to say this is only true for angular displacement, because it's true for both. Therefore, I can't call this either as linear displacement or angular displacement. That's why they call it, not late, Lagrange called it generalized coordinate. That means it can be whatever the displacements you want to consider, either as linear or angular. Therefore, he combined these two equations into one form. As long as you follow this definition, you can apply it to angular motion or linear motion or general motion. You can put these two combined together. It'll work out. So these are the three most powerful energy methods in dynamics. And why do we need energy methods? I know that in this dynamics, we didn't really explore the true power of energy methods, because most of the powers can be solved by what we call kinetics. That is essentially force equilibrium and moment equilibrium, right? Of course, that's important for now, but to some point, you will realize that some of the problems, you may not be able to find out what are the forces. What kind of problems can we use energy methods in dynamics or structural dynamics? One good example is what we call indeterminate systems or indeterminate structures. For mechanical engineers and civil engineers, this is a very popular case. So what's indeterminate structures? Indeterminate structures mean this. Suppose I have a beam. And the beam is, of course, supported by the support. And suppose there's a force here. And you call this point A, point B. Now, from structural analysis, you know that if this is a two-dimensional structure, we have three equations we can use, which is defining the x and y. You have summation of fx to be 0, summation of fy to be 0 and summation of moment z to be 0. This is for statics, right? Correct? From static, we learned this. Now, from dynamics, you must know this. From dynamics, if you're considering the dynamic equilibrium, this is not our Garvin equation. Our Garvin equation becomes this. Summation of fx becomes what? Equal to mass times the linear acceleration in the x direction. So it's m times ax. Right? Summation fy becomes what? Equals the mass times ay, linear acceleration in the y direction. What about the moment? Moment becomes here, if z is iz times alpha z. Right? But remember, there's a general form. So what's the general form? Minus ix minus iy times omega x times omega y. This is what I told you maybe last week, right? The most general form in dynamic. In dynamic equilibrium, these are the three Garvin equations we live with. Not like in statics. In statics, you have the three. So this is statics. And this side is dynamics. You must understand the difference. And which is why you need to take dynamics, because you already know how to do this. Force equilibrium, moment, force, all together will be 0. But in dynamics, you have to consider the dynamic quantities, acceleration, linear, angular, and also velocity, angular here. Fundamental difference between these two. Now, what is indeterminate structures? If I have 3 equations, that means I have 3 conditions. As for 3 conditions, you can only solve for 3 unknowns, right? Which means here, if I want to figure out the force here, you can determine only 3 parameters, 3 unknowns from here. Either it's reaction, Rxa, or Rax, this is Rbx, and because this point can move, so there's no horizontal force, and there's another one, which is Ray. The 3 forces you can find is Iy, Ix, and Rbx. Only 3 of them with the 3 conditions. No more. And from structural analysis, some of you, if you are curious, you may wonder this. Because the 2-dimensional structure, so I always have only 3 Garvin equations. That means I always have only 3 conditions. But what happens to this? What if I have a beam? Consider that this is the bridge, right? What if I want to add something to the beam? Can I do that? Of course. What if I said I'm going to add a spring here? Can I do this? Of course I can do it. Right? Now in this case, how many unknowns I have? At point A, this point B, and point C. At point A, I have R, A, Y, R, A, X, R, B, Y, and here at point C, I have R, C, Y. Now I have the force unknown. Right? So here, in this kind of problem, you have 4 unknowns, but the conditions that you have from force equilibrium is still 3. This is what we call indeterminate structures. The number of unknowns is greater than the number of conditions. This, unfortunately, you will always have 3 for planar structure. For 3-dimensional structure, you have 6 conditions. That means you can solve for 6 unknowns. That's why some of you from civil engineering, you will continue your study in structural analysis by using different techniques to figure out how do I solve these kind of structures. My point is, in some of the structural analysis, you may not see the sign or the values of the force that easily. Like this, indeterminate structures. You only have 3 conditions, but you have 4 unknowns. This actually could be difficult for you to solve for the forces. But if you use energy methods, you don't have to worry about this, because energy methods concerns only about the total energy of the entire system. It doesn't matter which force you are looking at. You just put a symbol, calculate them, and you differentiate them. So that's why I said the power of energy methods can be very, very in the long run, and you can use it for many different problems in your career. Now, example 36. So what's example 36? Example 36